So we have three figures here, figure A, figure B, and figure C. They all have two metallic spheres, and then we have a glass rod that's positively charged. So, yeah, we're considering the three figures below, and we'll start with part A. It says, what would happen if the rod were removed before the spheres are separated? So essentially, we're between step A and step B of what's going on. So what's happening is initially, right now we're solving for part A. Initially, when you bring the positively charged glass rod at a distance from sphere A and sphere B that are touching each other, in a previous video I showed that we would have negative charges on one side for sphere A because the negative charges are trying to move towards the positive charges in the glass rod, and then we'd have some positive charges left over here, and similar with sphere B where we'd have negative charges left over here. Now the two spheres are touching, so what's going to happen is that, and these two spheres are metallic, they have valence electrons, and the metals always tend to donate electrons. They're electron donors. So sphere B is going to donate electrons to sphere A just to try to neutralize at least one of its sides, I guess you could say, or one of its regions. And same for part A. Same for sphere A. Sphere A will also try to at least neutralize one of its regions, if not the entire sphere. So as the electrons flow from sphere B, the left-hand side of sphere B, to the right-hand side of sphere A, if we continue to allow that to happen, at the end we'd have a neutral area, neutral region here, and a neutral region here. And we're left with negative charges here on this side and positive charges there on that side. Now in this question we're trying to so that's what would happen. And now when we get to this point, basically the spheres would now that these regions are neutral, the only thing that's left now is the positively charged glass rod that is trying to pull sphere A towards it, because sphere A only has negative charges left. And at the same time, the glass rod that's positively charged is pushing away sphere B because sphere B only has positive charges left over. So the glass rod is repelling sphere B while attracting sphere A. And in general, sphere A is negatively charged and sphere B is positively charged. But the fact that the charges are sort of focused on specific regions of the spheres causes like the strength of the glass rod, the positively charged glass rod that is still quite close to both of these spheres, to be stronger. So hence sphere A and B get pulled apart from each other. Now we're saying that we want to remove the glass rod before these guys are pulled apart from each other. So yeah, like in these two regions, what we're saying is that in these two regions the spheres have neutralized each other. That's not a problem. We're at that step. But we immediately after we remove the glass rod, so it's no longer there. So what we have now is two spheres in contact, still in contact with each other, whereas sphere A has negative charges and sphere B has positive charges. Since these two spheres are still touching and they're oppositely charged, the electrons in sphere A will sort of shift this way, and they'll start to flow into sphere B until sphere A and B both become neutral. So what happens at the end is that they become neutral and they're still touching each other. So yeah, the spheres would neutralize each other as they show there. So that was part A. Part B said, would the induced charges be equal in magnitude if the spheres had different sizes? So basically, yeah, we go through the entire process. I've showed this to you in a previous video. It's called charging by induction. Based off that video, at the end, yeah, we're left with two charges that are uniformly charged, and they have opposite charges. Charges of opposite sign. So in part B, what we're being asked is, like, let's say sphere B, instead of being this massive, it was a bit smaller, like this. What if it was this small, and sphere A was still that same size? Would the magnitude of the charges be different from each other? The answer is no, they wouldn't. Now the thing is, I have a smaller sphere here, so I'm trying to just make the charges like be all over the place, but it's kind of small, so that's why I drew them a bit closer to each other before. But essentially you'd have the same number of charges in each of the spheres. So that's 3, 4, 5, 6, 7. That's 7 charges here. There we have 5, so I need 2 more. So yeah, so that would be sphere B. So yeah, the induced charges would be equal in magnitude to each other, even if the sizes of the spheres would be different. And that's just because, like, we don't really care about the region or the area or the amount of space the charges have. We care more about the fact that one electron will neutralize one positive charge. One negative charge will neutralize one positive charge. And basically, I'm kind of hinting at the fact that you can never have 1.5 negative charges. You can only have a whole number of charges. So, and since we have 7 charges here, we have to have 7 there. It's kind of to do with the law of conservation of charge, basically. That's why. So that's part B for us. Now, moving on to part C. So again, this is figure A, B, C, and we're just seeing different steps of how two metallic spheres are charged. Now, part C says, is there something slightly misleading about the figure C? So again, we've charged both these metallic spheres by induction, and now we're left with the two spheres at the end. They're uniformly charged. One is negative and one is positive. Is there something misleading about this figure, this step here, or this result? The only thing I would say is the fact that negative and positive charges tend to attract each other, right? Opposite charges attract. So the spheres are distance-wise, they should be a bit closer to each other. So what I'm trying to say is that since the two spheres will attract each other, they won't touch each other, but they still would attract each other to some extent. So they would be a bit closer in distance to each other, and also, like, the negative charges wouldn't be, nor would the positive charges be uniformly distributed like this. They would be more like something like this. The negative charges would be focused more on kind of one side. And same thing for the positive charges. They would be sort of focused more on one side. Again, I'm not keeping track of the number of charges here. They should be equal to each other, but I'm not focusing on that. So yeah, this is what would be the case. The distance would be a bit closer between the two spheres, and the charges would not be equally distributed in each sphere. They would be sort of concentrated in a certain region because opposite charges attract each other. So yeah, the charges from both spheres should attract each other and be a bit closer to the center of the image, hence the charges should not be evenly spaced out. Yeah, so that's what I was saying, so that's good, that's correct. Anyhow, I hope this video helped you guys. Have a good day.